Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is polynomials modulo and ideal. And the object of study in this video is a very special homomorphism from a polynomial ring over a certain ring to another polynomial ring, where now that polynomial ring is over that original ring quotiented out by some proper ideal. Okay, so let me do the setup here. So let's say we've got some ring, capital R here, and the only assumptions that we're going to make about this ring is that it's a non-zero commutative ring. Okay, so it's a commutative ring and it's not the zero ring. The zero ring, after all, is a bit boring. Okay, so we assume that it's not the zero ring because that one's a little bit trivial. Okay, so what we're then going to do is we're going to use this non-zero commutative ring to construct the ring of polynomials where the coefficients are taken from this ring, capital R here. Okay, so we're going to construct R adjoin X like so. Okay, now what we need is some proper ideal of this non-zero commutative ring R up here. So I'm going to have I is an ideal of R, and we're going to assume that it's a proper ideal, so it's properly contained within the ring. It is not the unit ideal. Okay, it's not equal to the entire ring. Now what we're going to consider is a homomorphism. Okay, and I will prove that this is a homomorphism, a mapping from the polynomial ring R adjoin X here into the polynomial ring where the coefficients, instead of being in the ring capital R, are instead in the quotient ring R quotiented out by I. Okay, adjoin X like so. Okay, so this is the homomorphism that we are going to be considering in this video. This is what polynomials modulo and ideal is all about. Okay, we're going to take polynomials where the coefficients are in the ring capital R, and we're going to turn the coefficients so that they're now modulo and ideal. They're now what they are in the quotient ring where the ring's been quotiented out by this ideal. And I'll stress again that this is a proper ideal, so when we quotient R out by I, we do not end up with the zero ring. Okay, if I was equal to the unit ideal and we quotiented R out by the unit ideal, of course we'd end up with the zero ring, and that's a very boring polynomial ring to be considering here. So we're going to assume that I is a proper ideal. So let me just add a few little notes on here. So I is a proper ideal here, that's an important point, and of course we're assuming that R here is a non-zero commutative ring. Okay, so the first thing then that I want to do is make this mapping phi precise. So I want to tell you exactly what it is actually going to do, where it's going to send an arbitrary polynomial in this polynomial ring R adjoin X here. Okay, and then what I want to do is, after giving you a basic example of this mapping, what we'll then do is prove that it is indeed a homomorphism, and then later on we'll have a look at why this is actually useful. Okay, we'll have a look at how this is very useful for finding out whether a certain polynomial in a ring of polynomials is irreducible or not, which is a question that we do care about. Okay, so firstly then, let's make this mapping precise. So let me tell you exactly where we're going to send any polynomial from this ring of polynomials where the coefficients are in the ring capital R into. Okay, where we're going to send it. So phi then, this mapping, is going to take an arbitrary polynomial. So an arbitrary polynomial will look like this: the sum over I of ai times x to the I here. Okay, so this is just a polynomial, and of course only a finite number of the coefficients will be non-zero, okay, because we're in algebra, not analysis. Okay, so we've got an arbitrary polynomial here, and of course all of these coefficients are from the ring capital R. Okay, so where is this polynomial going to be sent by phi? Well, it's going to be sent onto a polynomial in R quotiented out by I adjoin X here, so the polynomial ring where the coefficients are in this quotient ring are quotiented out by I. Okay, so we're just quite simply going to send all of these coefficients onto what they are in the quotient ring R quotiented out by I. Okay, so let me make this precise. We're going to need another homomorphism here, something that we already know is a homomorphism, and I'm going to use my favourite Greek letter zeta to represent this homomorphism. So zeta is another homomorphism, and zeta is going to represent the homomorphism from the ring capital R into the quotient ring R quotiented out by I, and we're going to need zeta in order to define phi up here. Okay, now of course the way that zeta is going to work is it's going to be the most natural homomorphism, okay, the one which the first isomorphism theorem of rings tells us all about, okay, and it's going to be the ring homomorphism which sends any element of the ring, so any little a which is in the ring capital R, onto the coset that contains the a bar here in the quotient ring here. So when of course you quotient out by the ideal I, you split R up into the additive cosets of the ideal capital I, and those additive cosets become the elements of the quotient ring. So quite simply you're going to send any element onto the coset that contains it in that quotient ring. Okay, and we know from having studied quotient rings that this is indeed a ring homomorphism. Okay, and we're going to need the fact that that is a ring homomorphism in the proof that phi is going to be a ring homomorphism. Okay, so now at the moment though we're just using this to define phi. Okay, so quite simply we're going to map our polynomial here onto the polynomial, the sum over I, and we're just going to send all of these coefficients onto what they would be sent by this mapping zeta here. So we're just going to take zeta of ai here, and then of course we'll just put that in front of x to the power of I, like so. Okay, so this is the way that I am going to define this mapping phi. It's just going to take an arbitrary polynomial, and it's going to go through all of the coefficients of that polynomial, which were originally in the ring capital R, and it's going to say, what would this be mapped onto in the quotient ring? What coset is this in the quotient ring? Okay, I'm going to reduce it modulo the ideal, basically, and now I've got a polynomial where the coefficients are all in this quotient ring, a polynomial where the coefficients are modulo an ideal, hence the title of this video. Okay, so to make this concrete then, let's actually look at a concrete example, and everyone's of course favourite example of a concrete example would be to use the non-zero commutative ring, which is the ring of integers. Okay, so let's use the ring of integers. So let's take some polynomial in the ring of integers and let's reduce it to modulo an ideal. So where shall I actually do this? So let's have phi going from the ring of polynomials with coefficients in the integers into, now which ideal shall I choose? Shall we just have modulo out by 3 times z? So the principal ideal generated by 3, all multiples of 3. Okay, and we're now going to have this polynomial ring where the coefficients are in z mod 3z here. Okay, so what I want to do then is do an example of actually taking a polynomial from the ring of polynomials with coefficients in the integers and taking it onto what phi would map it onto with this definition here. Okay, so let's just make up some polynomials. So let's have 9x cubed plus, what else should I go for, 5x squared. Let's have plus negative 2x. And then, what else should we have? Plus 1, let's say. Okay, so this is certainly a polynomial in the ring of polynomials with coefficients in the integers. You can see that all the coefficients here, 9, 5, negative 2, and 1, those are all integers, so this is certainly in the ring of polynomials with coefficients in the integers. Now let's ask, where will this polynomial be sent by our function phi? Okay, so it's now going to be sent into this ring of polynomials where the coefficients are in z mod 3z. Okay, so we just need to apply this rule here and send all of these coefficients onto what they would be mapped onto from this mapping zeta, which would in this case, and I'll just write this out, zeta in this case would be going from the integers to z mod 3z. Okay, so we just need to map all of the coefficients into what they would be modulo 3z here. Okay, so how is this going to work then? So, firstly, let's start off with this coefficient in front of x to the power of 3 here, the leading coefficient. So 9. 9 is obviously in the same coset as 0 in z mod 3z because it's a multiple of 3. Okay, so that would now become 0 in this new in this quotient ring here. So of course we don't bother to show terms which have 0 as their coefficient, so we wouldn't bother putting the third degree term anymore. 5x squared, now 5 is in the same coset as 2 in z mod 3z. Okay, so what this will become is 2x squared, so we might as well put 2 there. Okay, then negative 2, which coset is it in the same as? Well, if we add 3 on to negative 2, we get 1, so it's actually going to be in the same coset as 1, so this can be written as plus x, and 1 is obviously in the same coset as 1, so we'll leave that as it is. Okay, so here then, this is my polynomial now modulo this ideal 3z basically. Okay, so there is an example of what we're actually doing here. So we're just taking all of the coefficients and we're asking what are they mapped onto by this homomorphism zeta, and then we'll replace those coefficients like so, and now we end up with a polynomial where the coefficients are in the quotient ring. Okay, so the big thing that now needs to be proven is that this is indeed a homomorphism. Okay, so we need to prove that it is compatible additively, compatible multiplicatively, and then we also need to prove that the multiplicative identity is mapped onto the multiplicative identity. Okay, so those are the 3 criteria that a mapping must obey in order to be a ring homomorphism. Okay, so let's go then. So let's start with additive compatibility, and this has the potential to get very, very complicated. It isn't a complicated argument, but there are loads of additions and multiplications that are in loads of different rings. The thing is, we've got 4 different rings that are going to come into play here. We've got the polynomial ring, where is it? The polynomial ring with coefficients in R. We've got the ring capital R. We've got the quotient ring here, and we've got the polynomial ring over the quotient ring. Okay, so we've got 4 rings here, and I think it's important to pay close attention to when you are switching between the different rings. So I'm going to color code everything in, okay, because otherwise the argument can seem a bit lame unless you truly appreciate when we are making a jump into a different ring. Okay, so I'm going to color code everything in. So we will have our ring capital R denoted in green, I think. So all additions and multiplications that are in the ring capital R, I will colour in green here. We'll have the polynomial ring over with coefficients in the ring R, we'll have that denoted in purple. So when we've got additions and multiplications in that, we'll denote them in purple. Okay, we'll have the quotient ring R quotiented out by I. We'll colour that in, I think, orange. Okay, and then finally we'll have the polynomial ring with coefficients in the quotient ring. We will denote that in red here. Okay, this will help, and this will make the argument seem less trivial. Okay, if you don't stress all of this, then I think it does appear a bit lame. It appears a bit trivial. You don't really see the argument for what it really is, how clever it is, really. Okay, so I enjoy color coding it all in and seeing exactly when I'm moving from ring to ring. Okay, so we're going to do that. We're going to do it my way. Okay, right. So let's now check additive compatibility then first. So what we want to check then is that if we take phi of one polynomial plus another polynomial, so remember our mapping is from the ring of polynomials R adjoin x to the ring of polynomials R quotiented out by I adjoin x. Okay, so we need to check that if we take 2 polynomials in here, okay, and we add them together, so let's put this down. So let's say we've got a polynomial A here, which is the sum over I, AI, xi here, and we are now adding it in the initial ring of polynomials. So this is addition in the initial ring of polynomials, so I'll colour it in purple there, and we're adding it to another polynomial, which will be the polynomial b, so this will be the sum over I of bi x to the I here, and I want to prove that this gives me the same answer. So if I add these two together firstly in the ring of polynomials over the ring capital R here, and then map it into the ring of polynomials over the quotient ring here, that I get the same answer as if I firstly map each of these into the ring of polynomials over the quotient ring here. So I take phi of the sum over I, AI, xi here, okay, and then add it to phi of the sum over I, bi, x to the I. Now where is this addition? This addition is now in the quotient rings polynomial ring here. Okay, so this needs colouring in red here, like so. Okay, so I'm firstly mapping these two polynomials into what they are in the polynomial ring over the quotient ring, and then I'm adding them together in the polynomial ring over the quotient ring. Okay, right, so let's now prove that this is the case. So this is what we need to prove, so I should probably put a question mark there. We need to ask whether it is true, and this needs to be true no matter what polynomial you take here and no matter what polynomial you take for this one. Okay, so let's start off with the left-hand side and try and, well, we'll develop both of them and try and get them to meet in the middle. Okay, so let's start off by developing the left-hand side here. So firstly, what we have to do is add these two polynomials together. Now we know the way that we add polynomials together. We do it component-wise. We add the components. Okay, so this is going to become phi of the sum over I of AI plus bi, and this is why I think it's really important to colour code it, because now what's this plus here? It's no longer plus in the polynomial ring. This has become addition in the initial ring, capital R. So you add the coefficients that are in front of the same power of x in the initial ring, capital R here. Okay, so that's become a green plus here, and then it will be in front of x to the power of I, like so. Okay, so that's just the definition of addition in a polynomial ring. Okay, now we can apply the definition of phi to this. Okay, this is just going to be the sum over I of zeta of these coefficients. So the homomorphism zeta, which is from the ring capital R to the quotient ring R adjoin R, sorry, R quotiented out by I, we can now apply this. So zeta of AI plus bi times x to the I, like so, where this is still addition in our initial ring, capital R here, so I'll still colour code that in green. Okay, now what can we do here? We can now apply the fact that zeta is a ring homomorphism from R to R quotiented out by I. Okay, and we can now apply the fact that addition is compatible between the two. Okay, so we can now split this up like so, and I'll write this over here. It'll now become the sum over I of zeta AI plus zeta bi, okay, and then all in front of xi, and now this addition will be addition in the quotient ring, R quotiented out by I, so I'll colour that in green. And you should note that when we moved from here to here, we went from, well, this was a polynomial in R adjoin x. This is now a polynomial in R quotiented out by I adjoin x. Okay, and now all I've done is split up the coefficients in this way, which is perfectly valid. Okay, instead of adding AI and BI together in the initial ring capital R and then taking zeta of this to get something in R quotiented out by I, instead I have mapped firstly both of these into R quotiented out by I, and then I've added them together. So this is still something that's in here. Okay, now let's develop this side a little bit and show that it's actually going to be equal to this. So if I firstly do this side here then, okay, so phi of this polynomial here, just by definition, that will be the sum over I of zeta AI x to the I, and note we have now taken this polynomial which was in R adjoin x, and now this thing here is in R quotiented out by I adjoin x. Okay, and then we're going to add this in R quotiented out by I adjoin x here, so I'll put the red plus sign there, to the polynomial which is the sum over I of zeta of bi x to the I here, which is another polynomial in R quotiented out by I adjoin x here. And now we can just apply the definition of addition in R quotiented out by I adjoin x, which is you just take the coefficients and add them together in the ring which the polynomial ring has coefficients over. Okay, so you'll add the coefficients in here, and of course that's exactly what you've got here. Okay, so I've taken this side, turned it into this side, taken this side, turned it into this side, so the two sides do converge on one another, so I can conclude that this equals is correct here. Okay, so I'll put a tick by that. So addition is compatible between the two. Okay, so we've got additive compatibility, so this is looking hopeful. Now let's do the same thing but with multiplication. Okay, a slightly more difficult argument, but not much more difficult. Okay, and with colour coding it will become nice as well. Okay, so we want to prove, and I'll try and get this all on one page, so I'll try and squeeze it in down here, and I'll just move this up. Okay, so we want to prove that if we take phi of, and now we need two polynomials multiplied by one another, so the sum over I, ai, x to the I here, multiplied, and I'm actually going to put the multiplication symbols in as much as possible, okay, to make it absolutely clear, by another polynomial, the sum over j, and it's best to now have a different index for multiplication, bj x to the j here. Okay, and of course this multiplication here is multiplication in the initial polynomial ring, and I'll try and get it so our colour key is still visible up there. So we're taking phi of these two polynomials multiplied together in the initial polynomial ring R adjoin x here. Okay, and we want to prove that this will have the same answer as if we firstly map both of these polynomials into R quotiented out by I adjoin x. So we take phi of the sum over I ai x to the I here, and we multiply that in this polynomial ring R quotient out by I adjoin x. This is going to be a red multiplication sign here with this polynomial mapped into R quotient out by I adjoin x. So phi of the sum over j bj x to the j here. Okay, right. So we want to prove that this is true, and again I should put a little question mark above there because we don't know that it's true, we want to show that it's true. Okay, so same tactic, we're going to firstly take on the left hand side, work with it a little bit and try and then develop the right hand side so that they converge on one another, so that they're equal to one another. Okay, so let's start with the left hand side again. So we need to remember the way that we multiply polynomials together in a polynomial ring. Remember, the way that we do this is we firstly define how monomials multiply, and monomials multiply by just taking the two coefficients, multiplying those two together in the ring that the polynomial rings over, okay, and then just adding the powers of x, okay, so that's how monomials multiply. Then what we do is we imagine taking these polynomials and viewing them as a real sum in the polynomial ring of their monomials. So we decompose them into their sum of monomials. Okay, so the meaning of the sum changes basically. Here, initially, when you think of polynomials, where you've got this sum here, it really just tells you how to generate a symbol. Okay, it just means create the symbol that has all of these terms with plus symbols in between them. Okay, but it is just a symbol in this mathematical structure which is the polynomial ring. Okay, now in order to define multiplication, it's best to think about decomposing this into a sum of monomials, so actually thinking about it as lots of monomials added together with the definition of addition that we've defined on the polynomial ring. And then what you can do is you do this for both of them, and then you get a huge, great big sum. And then because you want it to be a ring, you want it to obey distributivity. So you can then just apply distributivity and reduce it into loads of monomials multiplied by each other. And then you just have to sum back up all of the monomials. Okay, so we're going to change the meaning of addition basically. We're going to go from just viewing it as a symbol to actually viewing it as a real sum in the polynomial ring. Okay, so I'll underline it in yellow to show that we've now changed its meaning, and I'll also double underline it with a purple here because we've changed it into a sum of monomials in the polynomial ring R adjoin x. Okay, because later we're going to do the same thing over here, but it's going to be in the different polynomial ring, so I think it's best to double underline it. The yellow shows that we've changed the meaning of the sum here, rather than it just being symbolic, to actually meaning sum in the polynomial ring, and the purple denotes the fact that it is summation in the polynomial ring R adjoin x. Okay, so now what we can just do is apply distributivity here, okay, and multiply all the monomials together, so this will become phi of, and then we'll get the sum over I, the sum over j, okay, and these are still real sums. These are sums in the polynomial ring, so I'll underline them in yellow and purple again. Okay, it's a real sum, not just a symbolic sum of, and now the way that you multiply the monomials is you multiply the two coefficients together, so ai and you multiply that with bj, and the way that you do that is in the initial ring, so I'll colour that in green there, that's multiplication in the initial ring, and then you add the powers of x to the I plus j. Okay, so now you've got the answer to this, but as a sum of a huge number of monomials. So in principle, what you could do is you could use the definition of addition in the polynomial ring to sum all of these monomials together and get the answer as to what these two are multiplied together. So that's the way that we define multiplication in our polynomial ring. We define how to multiply monomials, and then we just note that all other polynomials can be written as a decomposition of a sum of monomials, and then if we want distributivity to be true, we're stuck then as to how all polynomials must multiply. You just decompose them into their monomial sums and then apply distributivity and get a whole great big sum of loads of monomials multiplied together. Okay, which is what I've got sitting in front of you here. Okay, so this is equal to this, and now we know, because of what I've just proven, that phi is compatible with addition. Okay, it doesn't matter if I firstly add things together and then apply phi, or if I firstly apply phi and then add them together in the in the codomain. Okay, now of course here it was only for two things, but once you've got it true for two things, you can extend it up very easily to an arbitrary string, a finite arbitrary string of things added together, which is what I've got here. I've got an arbitrary length finite, but I do know it's finite because of course only a finite number of these coefficients are non-zero, so therefore only a finite number of these products are going to be non-zero. So I do know it's a finite product here, and therefore I can now basically move the phi inside. Okay, and something subtle is going to happen here, okay, because this sum is now going to change from being a sum in the polynomial ring R adjoin x to being a sum in the polynomial ring R quotiented out by I adjoin x, but it's still going to be a real sum. So I'm going to notate this as so. Okay, it'll be the sum over I, the sum over j, and I'm going to have the yellow line to denote that it's a real sum, not just a symbolic sum, and now it's going to be underlined with red rather than purple because it's now a real sum in the polynomial ring R quotiented out by I adjoin x. Okay, and now it's going to become phi of all of these monomials. Okay, so you'll act phi on all of the monomials, but what is phi of a monomial? Okay, well, just applying the definition, it will be zeta of the coefficient of the monomial times by the power of x. So this will just become zeta of ai times bj, x to the I plus j, but note that we have done two steps there. Firstly, we applied the fact that we have additive compatibility here to move the phi onto just the monomials that are in this great big sum here, and then we applied the fact that phi of a monomial is just zeta of the coefficient times x to the I plus j. Okay, and this multiplication is still multiplication in the initial ring capital R. Okay, now of course what we can do is apply the fact that zeta here is a ring homomorphism from R to R quotiented out by I, so this is going to be the same as the sum over I, the sum over j of, and now what we'll get is zeta ai multiplied by zeta bj, all in front of x to the I plus j. Now let's colour this in. It's still a real sum here, so this is still underlined in yellow, and it's still a real sum in the polynomial ring R quotiented out by I adjoin x. Okay, this multiplication here is now multiplication in the quotient ring R quotiented out by I, so I'll colour that in orange there. Okay, now what we have to do is go to this right-hand side and turn it into this, show that it's equal to this. Okay, so this isn't too difficult. So firstly, we just apply what is phi of this thing. Okay, so by definition, phi of this polynomial is just going to be the sum over I of zeta ai x to the I, like so, and then we want to multiply it in, of course, our polynomial ring R quotiented out by I adjoin x, with this polynomial here, which will be the sum over j of zeta bj xj. Okay, So that's equal to that. Okay, now what we do is we just apply the definition of multiplication in our polynomial ring R quotiented out by I adjoin x, and we do it in the exact same way as we did here. So we stop viewing these sums as just symbolic, we start viewing them as real sums. So we view this as a real sum, and this is a real sum, and of course they're real sums in the polynomial ring R quotiented out by I adjoin x, so I'll underline them in red there. And now what we do is we have them as decomposed into these monomial sums, and now we just apply distributivity. So of course, if you apply distributivity there, you'll get the sum over I, the sum over j, you'll multiply the coefficients together. This is the way that you multiply monomials, so you'll multiply the coefficients together in the ring which the polynomial ring is over, which is R quotiented out by I, which is exactly what we've got here, and you'll add the powers of x together, which is what we've done here. Okay, so indeed we have shown that we can go from here all the way back to here, so we have shown that multiplication is compatible in this way. So this is looking very, very good. One final thing that we need to show is that the multiplicative identity is going to be mapped onto the multiplicative identity by this mapping phi. Okay, so we need to make sure that the multiplicative identity in this polynomial ring, which is just the constant polynomial with 1 as its coefficient, okay, so you take the multiplicative identity in the initial ring, put that as the only non-zero coefficient in the constant portion, okay, and that will be our multiplicative identity in this polynomial ring, and the same will be true over here. It'll be the multiplicative identity from R quotiented out by I, and then just that as the constant polynomial. So what we want to make sure of is that this is mapped onto this over here. Well, what is phi of the one polynomial going to be? Well, of course, you're just going to take zeta of 1, okay, because you'll just apply the definition, where is it now, this here, okay, you've only got one non-zero coefficient, which is the constant coefficient here, okay, which is 1, but you'll just apply the definition here, and you'll just say, turn that coefficient into what zeta of it is, okay, so it will be mapped onto zeta of 1 here. But where will zeta send 1? It will send 1 onto the coset that contains 1. Okay, and of course, because this is a ring homomorphism, it will always have to send that onto 1 in the quotient ring R adjoin I. Okay, so because this is a ring homomorphism, this will indeed have to be 1 in the quotient ring R adjoin I, so you will end up with 1 in the constant portion of this polynomial. Okay, so it will actually work. The multiplicative identity in this polynomial ring will be mapped onto the multiplicative identity in this polynomial ring. Okay, so this mapping is indeed a ring homomorphism. Okay, so you can always establish a nice mapping then from a polynomial ring over the ring capital R into the polynomial ring R quotiented out by a proper ideal capital I adjoin x. Okay, and you map all polynomials onto what they are when their coefficients are taken modulo that ideal. Okay, so it's very, very interesting. Now, what I want to show you in the next video is why do you actually care? Why should you actually care? What is this useful for doing? Okay, and we'll see how it's useful for finding out whether a polynomial in a polynomial ring is irreducible or not.